Welcome to the Explainer. Today we're doing something incredibly exciting. We are booting up a high-tech holographic wave simulation. We're going to track the complete life cycle of a single wave, from the very moment of its birth in the deep ocean all the way to its spectacular, crashing demise on the shoreline. This is all about uncovering the hidden physics, moving silently right beneath the surface. Okay, let's dive right into this. Here are the core parameters for our digital ocean today. Section 1, the birth of waves. 2, anatomy of the deep. 3, wind waves and swells. 4, collisions and rogue waves. 5, the surf zone break. And finally 6, the tsunami threat. Section 1, the birth of waves. Before a wave can even begin to travel across our simulation, we have to generate a disturbing force. Take a look at how wave energy is distributed. Different forces generate entirely different types of progressive waves. Tides, for instance, they're driven by the gravitational pull of the moon and sun. Tsunamis are sparked by massive seismic events like earthquakes. But as you can clearly see, wind-generated waves provide the vast majority of all the wave energy distributed throughout our oceans. So, the absolutely crucial takeaway here is this. Waves are moving energy. They travel right along the interface between two fluids, in this case, the atmosphere and the ocean. When you're standing on the beach watching a wave roll across the water, you aren't actually watching a chunk of water travel from point A to point B. No way. You are watching pure energy move through the water. The ocean itself is literally just acting as a transfer mechanism. All right, moving on to Section 2, anatomy of the deep. Let's zoom way in to look at the exact anatomical measurements of a single wave. As this wave energy moves through, the individual water particles themselves are set into motion in a circular pattern. We call this an orbit. The highest point is your crest, the lowest is the trough, and that horizontal distance between them, that's your wavelength. We also measure its frequency, which is just how many waves pass a fixed point per second. But notice what happens below the surface here. Those circular orbits decrease in diameter until they vanish entirely, at a depth equal to exactly half of the wavelength. Below that line, the water is perfectly undisturbed still. Kind of wild, right? Now, what's really interesting about this is how we track it. A crucial measurement for tracking this energy is celerity, the precise speed of the wave. We calculate this simply by dividing the wavelength by the wave's period. And the period, the time it takes for two consecutive crests to pass a fixed point, is actually permanently fixed at the wave's birth by whatever disturbing force created it. So by calculating celerity, we can accurately track our wave's speed as it races across the water. But ocean depth really dictates the vital math here. In a deep water wave, where the depth is greater than half the wavelength, those circular orbits don't touch the bottom at all. But in a shallow water wave, where the depth is less than 1/20th of the wavelength, the seafloor brutally interferes. It physically flattens those circular orbits into ellipses. This friction literally determines the speed of the wave, slowing it way down as the water gets shallower. Section 3, wind waves and swells. Let's fast forward our simulation a bit and watch how our freshly birthed deep-water wave actually grows and travels across the vast open ocean. Our wave grows in a very specific sequence. Step 1. Wind friction creates tiny ripples called capillary waves. Step 2. If the wind keeps blowing over an uninterrupted distance, a vital parameter we call the fetch, it grips those ripples and builds them up into much larger gravity waves. And finally, step 3, because longer waves have higher celerity, they basically outrun the shorter ones. This process, called wave sorting, eventually organizes those chaotic, stormy waves into the clean, rhythmic, long-period lines that we just call a swell. Okay, here is where the physics get completely mind-bending. Look at the sequence of a wave train leaving the storm area. As the group moves forward, the leading wave constantly transfers its energy downward into the undisturbed water, and it essentially dies out. To replace it, a brand new wave forms at the very back of the pack. Because of this continuous birth and death cycle, a wave train as a group actually moves at exactly half the speed of the individual waves traveling inside it. Of course, the ocean isn't exactly an empty highway. Section 4, collisions and rogue waves. Our wave is about to encounter some serious obstacles as overlapping swells from entirely different storm centers start crashing into each other. When these swells collide, we get interference patterns. Constructive interference happens when the crest of one wave perfectly aligns with the crest of another. Their energy is literally added together, creating a much bigger wave. On the flip side, destructive interference happens when a crest meets a trough. Their energies subtract, essentially canceling each other out and leaving a flat surface. And this brilliantly illustrates precisely why waves behave the way they do at the beach. Because of these overlapping waves moving into and out of phase, we get this alternating pattern. It's exactly why surfers experience waves coming in sets of maybe 5 to 7 large, rideable waves, followed by a frustrating lull of smaller, destructively interfered waves. But when constructive interference goes to the absolute extreme, we get something terrifying: rogue waves. These are massive, isolated ocean waves that seemingly appear out of nowhere. Sometimes it's just perfect storm interference overlapping just right. Other times, it's strong ocean currents amplifying an opposing swell. A very real-world example of this happens off the southeast coast of Africa. There, the incredibly fast Agulhas current violently rams into huge swells moving up from Antarctica, amplifying them into sudden, sheer, ship-breaking rogue waves. Absolutely massive. Well, we've survived the deep. Section 5, the surf zone break. The deep water physics we've been tracking so far are about to violently shift as we hit the coastline. You see, the slope of the seafloor dictates exactly how a wave will break and expend its energy. A gently sloping, flat bottom creates a spilling breaker, which causes the wave energy to just gradually spill down the front face. But a steep bottom? That creates a plunging breaker. The ocean floor rapidly slows the bottom of the wave, throwing the crest forward into that beautiful, fast-curling air pocket that surfers absolutely love to ride. And then we have this chaotic scenario, the surging breaker. If our simulated wave hits a highly abrupt, very steep shore, it literally never gets a chance to properly break. The wave energy just violently and instantly surges right up the beach. These waves don't curl, they rapidly lose their structure, and yeah, they are completely unsurfable. But the coastline doesn't just break waves. Its geometry completely scrambles incoming energy through some pretty complex behaviors. We have refraction, which is the wave bending because the part that hits shallow water first slows down while the rest keeps going fast. Then there's reflection, where the wave simply bounces backward with very little energy loss off a straight vertical barrier, and diffraction, which is the energy spreading out sideways as a wave tries to squeeze past or around an obstacle in the water. Let's see how this builds when reflection creates a standing wave. When a reflected wave perfectly overlaps an incoming wave of the exact same length, the water stops moving forward altogether and just oscillates vertically. The nodes are dead zones with zero vertical movement, while the antinodes are the exact points of maximum, dramatic water flow, just rising and falling. Okay, we've seen what wind can do. Section 6, the tsunami threat. Let's override the system and run a catastrophic seismic displacement scenario. 200 meters per second. That is roughly 720 kilometers per hour. As we know, a tsunami is triggered by massive, rapid water displacement, like an earthquake suddenly dropping the actual ocean floor. Because they have these incredibly massive wavelengths of 100 to 200 kilometers, they always act as shallow water waves, even in the very deepest parts of the ocean. Their incredible speed is dictated solely by the depth of the water. And that leads to their most stealthy and honestly most dangerous characteristic. Tsunamis hide as incredibly small waves in deep water. Out in the open ocean, the height-to-length ratio is so tiny, a ship might not even notice a tsunami passing rapidly underneath it. But the moment that massive wavelength hits the shallow coastal shelf, all that 720 km/h speed is instantly converted into devastating, terrifying vertical height. Which brings us to the end of our digital model today and leaves us with a critical question to consider. As we map these parameters, how prepared are we to detect and survive the raw, invisible power of these massive oceanic forces? We understand the precise physics of waves, the celerity, the interference, the depth ratios, but the ocean remains a volatile, awe-inspiring force that demands our utmost respect. Thanks for joining me on this explainer, and I hope you never look at the beach the same way again.